Just as an introduction, my name is Glenn Arthur. I'm the current chair of the RACI Chemical Education Group here in South Australia, and we welcome you all to the Stranks Memorial Lecture for 2021. We've got our international guest, Professor David Leigh, with us this evening, and I'll get Hamish to introduce him in a moment. Just a little bit of detail about these lectures. Some people may not know who Professor Donald Stranks was and his relationship to both the University of Adelaide and to South Australia and chemical education. So these lectures commemorate Professor Stranks, who was head of physics and inorganic chemistry at the University of Adelaide from 1964 to 1973. He was then Vice-Chancellor from 1977 until his passing in 1986. And he was our founding chair of the RACI, Royal Australian Chemical Institute Chemical Education Group, so the group that I'm chairing now. He was born in Melbourne, Victoria, commenced his PhD from the University of Melbourne in 1954. And as a scientist, Professor Stranks was a leading member of the Australian and International Inorganic Chemistry Community. In 1955, he was awarded the Rennie Memorial Medal of the Royal Australian Chemical Institute for his research in radioisotope and radiation chemistry. In recognition of his substantial contributions to inorganic chemistry, Stranks was the recipient of the Burroughs Award for Inorganic Chemistry in 1977. So we're absolutely delighted this evening to announce Professor David Leigh as our esteemed keynote. And I would like to pass over to Hamish, Dr. Hamish McTurnan, another member of our ChemEd group, to introduce our guest.
Thanks, Glenn. I just want to put this in perspective of technology. In 1903, the Wright brothers, they couldn't have envisioned just how much their maiden flight had impacted our world today. If you think about that from the pandemic perspective, it's an even greater impact. Similarly, today's engineers of molecular machinery, they might not see the full impact of their research and the technologies that are in years to come. Over the last 34 years, David Leigh has had over 300 publications and 30,000 citations in the areas of supramolecular chemistry and molecular machines. David and his research group have had many firsts in the areas of molecular information ratchets, switches, knots, Walker track systems, robotics, and motors. These efforts have garnered them multiple publications in distinguished journals such as Nature and Science. I had the privilege of meeting David in 2014, where I found him inspirational, extremely humble, and very generous with his time. Could you please give a warm digital welcome to the 2021 DR Stranks Memorial Lecture guest speaker, Professor David Leigh.
Thank you. Thank you so much, Hamish, for that really kind introduction, and welcome and welcome everyone from what's the morning in Manchester. It's 8:30 in the morning here. I've just had my breakfast, so I'm all raring to go and delighted to be talking to you today. My great thanks to Glenn and Hamish and all the rest of the RACI Chemical Education Group for the honour of giving the Stranks Memorial Lecture this year. I'm so sorry that I can't be with you in lovely Adelaide. Obviously the pandemic precludes that, but we'll do our best to make the distance between us seem as little as possible. Right. I hope that I'm going to try and share my screen. I hope that that works. Just see how this is going. Paused. Hopefully that works. Glenn, can you just give me a thumbs up if that's working okay for you? Okay, great, then we can get started. So just before I start, I hope that some of you in the audience have got some of these, a couple of paper clips and some kind of banknote that we'll get to for just a little demonstration in 5 minutes or so into the lecture. But what I'm going to talk to you about today is the ultimate in miniaturization. shrinking the concept of a machine down to the molecular level. And before I start going into that in detail, I want to ask you a question that I like to ask my students in Manchester, and that is to try and think about what will technology be like in 40 years' time in the future. And this is a really hard question to answer with any kind of authority, because if you just look back 40 years to when I was at the age of many of you in the audience, just finishing high school, things were just so different to the way they are today. There were no computers, no internet. We only had 3 television channels here in the UK. We had black and white television when I was a kid. There was no Google, no Snapchat, no Instagram, no YouTube, none of these kinds of things. And even being able to predict those things in the future and how those would revolutionize the way that we live our lives today, it's sort of almost impossible to do it with any kind of success. And yet looking forward, trying to predict the future is important for scientists and society and for politicians, because it gives you a chance to try and steer towards the future that you want, be that making sensible decisions about climate change or pandemics or economics or equality. All those kinds of issues benefit from having some kind of forward vision, and science is no different. So if we want to try and predict the future, where it comes, particularly in something like technology, perhaps the best way to have some idea of how that might go is to look back and to think about what are the things that have influenced changes in technology over the years. And if we just think about computers, then at the end of the Second World War, some 60, 70 years ago, computers filled the size of a room, just like you can see here in that photograph in the top left hand corner of your screens. And yet today, all of us, all of you in the audience, have got far more computing power in every single sort of device that that we have, from your mobile phones to your televisions, the cars that you drive in. All of them have got far more computing power than these computers, early computers that filled the size of a room. And yet, of course, they're much smaller. All the microprocessors in your phones will fit on the size of a matchstick. They're absolutely tiny. And in fact, this miniaturization, the increasing miniaturization that we witnessed in terms of components for technology, is what has driven these incredible advances that we've seen today. And the ultimate in miniaturization, when it comes to machinery, is shrinking down machines and their components to the size of molecules. That's just a nanometer in size. A nanometer is a millionth of a millimeter. So that's a million times thinner than the thickness of a human hair. And the idea of shrinking machines to the molecular level was first discussed by a famous Nobel Prize winning physicist, Richard Feynman, at the end of the 1950s, in a lecture that he gave to the American Physical Society called "There's Plenty of Room at the Bottom," where he talked for the first time about the possibilities that could happen for when you shrink machines down to the molecular level, and the completely new opportunities for design and function that these kinds of nano machines could have. And in fact, there are these days there are high hopes for molecular machines and nanotechnology. Some people think that nanobots are going to go inside us, go inside the cells and be used to cure diseases at the molecular level by having molecular sort of size surgeons. However, other people are worried about the fears of what nanobots could bring. And there have been discussions about the possibilities, the theoretical possibilities of grey goo, self-replicating nanobots that could take over the planet and see the end of humanity as we know it. Even politicians are engaged in this discussion of the pros and cons of nanotechnology. And Buffoon that we have in Great Britain, in his first speech to the United Nations a couple of years ago, he discussed, at least briefly, nanotechnology and this dichotomy of, is it going to solve our problems to do with health, or is it going to leave tiny robots to replicate in the crevices of our souls? So when you've got people who are not scientists, very interested in this kind of technology, it falls on us as the experts in this area to try and explain to society about what we're doing, so that we can tell them about what are the scientific facts in this area and try and sort that out from the science fiction, so that politicians and society in general can make informed decisions on what's best to do with these kinds of technologies, and really what the state of the art is and the benefits that it can bring. And so what I'm going to try and talk to you about today is I'm going to show you what the state of the art in this field is, so that you're better informed as young citizens in this world of what you think the prospects are for this kind of science. So why do we think that it's possible to shrink the concept of a machine down to the molecular level anyway? Well, the answer is there already is a working nanotechnology out there, and it's called biology. And this slide really shows the reason why scientists at the start of the 21st century should be interested in trying to make molecular machinery. And that reason is because molecular machinery, molecular machines underpin all of life itself, all of biology, everything. So every single biological process depends fundamentally upon controlled molecular motion and molecular machines. So the way that energy is harvested from the sun, the way that it's stored in the cell, the way that it replicates, the way that your muscles move, the way that you're able to think, the way that you're able to see what's on the screen, all those processes depend fundamentally upon controlled molecular motion and molecular machines. In contrast, humankind at the start of the 21st century, we don't use molecular machines for anything at all. So polymer, every plastic, every pharmaceutical, every drug, every material, static or equilibrium properties to have function. And biology hasn't evolved to use molecular machines for everything for no good reason. And when we learn how Sorry, everyone, I'm back. Was that me just the link just getting dropped?
I think it was just the bandwidth potentially, yeah.
Okay, my apologies to that for everyone. Is that everyone back with me? Hamish, sorry, Glenn. Is everyone back and can see me?
Yeah, we've still got everyone logged in and back on screen.
So my apology. Yep. Okay, my apologies to everyone. So where I'm not sure where I actually got cut off. I was explaining about nanotechnology in the cell. Did you get some of that part and the importance of doing it with? Can you remember what I was saying when I got cut off? No.
I can't remember word for word.
Anyway, I hope no. Okay, the reason that scientists should be interested in trying to make molecular machinery is because of there already is this working nanotechnology called biology, and if we are going to make molecular machines ourselves, the reason for doing that is because of all the fantastic things that we can see that biology uses molecular machines for. Imagine if we could do similar sorts of functions with artificial machines, all the revolutionary technologies that could bring about. It would make the technologies that this thing would introduce, if we could make man-made molecular machines of this kind of sophistication, would be like things you see in a Harry Potter film. And in fact, scientists have started to try to make molecular machinery for the last 20, 30 years or so. And already the first Nobel Prize has been awarded in this area to three of my friends, three of the pioneers of this field, Jean-Pierre Sauvage, Sir Fraser Stoddart, and Ben Feringa, who received the Nobel Prize in Chemistry in 2016 for work that they did mainly in the 80s and 90s on just making the most rudimentary, the simplest kinds of molecular machines. And I'm going to bring you up to date on how we and others have have stood on their shoulders to make more sophisticated systems. This is some of the work that's been done from our group, and I'm just going to talk to you about a little bit of some of these systems today. In particular, this area new area of molecular robotics, programmable molecular machines, and you'll see at the top there, I've called it the bio-inspired nano machines. And the reason for that is because the way that we're going to have to design molecular machines is to use inspiration from biology, because the way that matter behaves at different length scales is just so different. So this mug of tea that I've got in front of me is a macroscopic object. So obviously it's in the big world. So if I put it on my desk, it's not going to move around. It's just going to stay fixed in place during my talk, unless I happen to knock it with my arm, give it some kinetic energy and send it sprawling across my desk and the tea all over the keyboard. But if this was a molecular sized object, it wouldn't be still at all, because if it was the size of just one or two molecules, it would be constantly moving through random thermal motion, something that we call Brownian motion, which is an intrinsic property of atoms and molecules that are at such a small scale. So if you're trying to design machines that work through movement, if they're at the molecular level, it's not like in the big world where you use engineering concepts that have to make things move. At the molecular scale, they're already moving. What you need to do then is a different engineering challenge. You need to control the directionality of this random motion so that you can use that to perform some sort of task. So that just illustrates how the problems of engineering machines at the molecular level are completely different to the problems that we face with engineering machines in the big world. So we have to learn a whole new type of molecular engineering strategy a whole new strategy for engineering at the molecular level so that we can design and build molecular machines. And because there is this working nanotechnology from biology, it seems to make sense to learn how biology makes machines that work at the molecular level and exploit those sorts of features in our synthetic designs. And I'm just going to talk about a couple of these sorts of points that we can take from biology. One of the things is that biology often uses architectures for its machines that restrict the degrees of freedom of the components to just a small number of dimensions. So the machines in biology often walk along tracks, move along tracks, or rotate around rings. But how do we make things that can be interlocked, threaded onto tracks or threaded onto rings? Well, biology also has a way of doing those sorts of processes. It uses something called self-assembly. And I wanted to illustrate what self-assembly is today through this very simple sort of illustration of the process. So hopefully some of you will have got these two paper clips that we're going to use as rings, that in order to make a molecular sized machine, we're going to want to link these kinds of rings together so that they can move in a controlled way with respect to each other. And to help us to do that, we're going to use a banknote. So I want you to take your banknote. I've got an American dollar here, but this will work with your very valuable Australian dollar currency. So if you have any banknotes, take that and just fold it into a Z or a Z type shape. So 3 folds or 2 folds so that you've got 3 layers. And then what I want you to do, I'm going to just pop on my one just a little rubber band so that my rings are going to get trapped and see what actually happens. You don't have to do that. But if you just take the note after you've got the folds, I want you to put 1 paper clip in between 2 of the folds. So the bottom 2 folds like that. I hope you can see how I've done that. And then I want you to take the second paper clip and to fit it over the second, third folds, so that you've got 1 paper clip over the first 2 folds, the second paper clip over the second 2 folds, over folds 2 and 3. So you should have a system that looks like that, other than having the rubber band. And now to make those 2 paper clips interlock, all you need to do is pull the banknote from left to right there. And you should have found that the 2 paper clips interlock together and thread together to form an interlocked structure. And now you can see that these rings can actually move because they're threaded with respect to each other, but they won't come apart. And this is an example of the sort of thing that biology does to self-assemble the components of machines. And we can do that sort of trick ourselves in the laboratory. And we discovered a way of doing that quite by chance in our laboratory some 25 years ago now, when we were trying to make just individual ring molecules. And we were trying to make an individual ring molecule that would actually bind to carbon dioxide. In the cavity here, we hoped it would be able to sequester CO2 from the atmosphere and perhaps be useful for sucking it out to help for global warming, the problems with global warming. However, when we tried to make these single rings in the laboratory, we got a surprise, because what actually happened was that 2 of these rings interlocked together, just like these paper clips do, because of hydrogen bonding interactions, the same sort of interactions that are present in water or in DNA or in proteins. In this case, they actually cause the rings to self-assemble to form these interlocked kind of molecular structures. And this is actually a picture of by formed by a technique called X-ray crystallography, which shows the precise positions of atoms in these molecules. And one of the rings is shown in the framework is shown with these light blue, in the light blue color, and the other ring, the framework of it is shown in this yellow color. And I hope that you can see that these really are interlocked together to form this these interlocked rings. And so, having found a way to form these threaded kind of molecules, we realized that we could perhaps use the fact that we got this threaded architecture to control the motion in these kinds of systems and try and mimic these amazing motor proteins and machines that you find in biology. And this slide shows an example of such a biological molecular machine. This is a motor protein called kinesin. That's the thing that's walking along the track. And this track is shown in the video is a microtubule. And the thing in the background is the nucleus of the cell. And what the kinesin is doing is it walks along the microtubule which leads from the nucleus to the extremities of the cell. And you can see that it's carrying a cargo in this sort of bubble in the top. And that contains proteins that have newly been built in the cell. So biology uses these kinds of walking machines, these walking proteins, to distribute newly made molecules around the cell. We wondered, could we make molecules that also move along tracks, such as these threaded ones that we've made? And this was a threaded molecule that we'd made that has a different function to kinesin, but I want to try and explain to you how it works. So these cartoon representations here are of the molecule that we've made, where we've got this ring locked onto a linear track, just like the kinesin molecule moves down the track. And on this track, we've got these F letters. These represent the element fluorine, or fluorine atoms. And these fluorine atoms are attached to part of the track. And fluorine atoms are like the constituents of Teflon. They're in the constituent of Teflon for non-stick pans. So if these fluorine atoms are exposed to the outside world, then the surface properties of when this molecule is absorbed onto a surface will be relatively hydrophobic, water hating, because it will be a greasy sort of surface. However, if we shine ultraviolet light on this system, we can cause this ring that's threaded onto the track to move down the track and cover up the Teflon-like group, the fluorine atoms, and hide them in the cavity of the ring here. And then, because the fluorine atoms can't see the outside world, the surface becomes less greasy, it becomes hydrophilic, water loving. And so the surface properties of this material can change just through the action of light on this material. And here's a photograph and some video of what you can do with this material. So this is the flat surface that you can see in front of you, coated with just a monolayer, one layer thick of these artificial molecular machines with the fluorine atoms on them. And on top of this flat surface, we've added a tiny droplet. That's this sort of black dome that you can see here. That's it's just a microliter droplet of liquid. And you can see it's just over a millimeter in diameter on the surface here. It's not water. Water would evaporate too quickly, so we have to use a high boiling point liquid. This one's called diiodomethane. And you can see that the liquid has quite a high contact angle with the surface here, because the droplet doesn't like the hydrophobic fluorine Teflon-like groups. Now what we're going to do with this system is just irradiate with UV light, not over the whole surface, but just the front edge of the droplet. And so in this region here, the surface properties are going to change. And what's going to happen is the fluorine atoms will be covered up. And this is a video of what happens when you do that. So we're just irradiating here with UV light. And so in this region, the fluorine atoms, the Teflon groups, are getting covered up. So then the droplet likes to wet that part of the surface more. And then after a bit, you can see that even the rear of the droplet is moving. So the whole of this droplet that you can see with your naked eye is being transported across a surface on a monolayer, one layer thick, of these artificial molecular machines just by the action of light on the surface. And you can, when the experiment is finished, you can see that the shape of the droplets change because it now wets the surface better. If you do the same experiment without the fluorine atoms, it doesn't work. So those are absolutely crucial. You can even use this to do work. So this is a 1 in 8 slope, which is probably more than I can do on a bicycle. But if you put the material on this 1 in 8 slope, put a droplet on it and irradiate the front edge of this particle, of this droplet, you can raise it uphill against the force of gravity just by the action of light on this monolayer, one layer thick, of these artificial molecular sized machines. Now, this is just a prototype experiment that we did some 16 years ago now in the laboratory. But what could this be used? Well, imagine you had a table like the desk in front of me or the desk behind me. Imagine if I put my coffee cup on that table and it was coated with a monolayer of these kinds of molecular machines, then maybe I could just use a laser pointer to move my cup around on that table. Nothing else, just the action of a laser pointer riding it across that table would be able to move a macroscopic object like a mug on this layer of molecular machines. That's not possible yet, that's not been done, but you can see it's been demonstrated there with a little droplet on this monolayer of molecular machines. That's the potential for what these things might be able to do one day. As well as using biology for the inspiration for how to design our molecular machines, we're also like to follow what biology uses molecular machines for in order to decide what we might want to do with molecular machines. And one of the things that biology uses molecular machines for, one of the most important roles, is actually to build other molecules. And this is the most amazing biological machine of all. This is the biological machine called the ribosome in the center of this slide here. And the ribosome is the molecule that's responsible for building all the proteins in the cell and in all organisms, in your body and in the flies, in vegetation, in bacteria, everything. And the way that it does this is it reads information that's on a tape that's come from the genetic code. So the genetic code, you might be aware, is transferred from in the form of DNA, and then the information from that DNA can be transcribed, can be written to other kinds of tapes. And this tape that's read by the ribosome is called messenger RNA, messenger RNA or mRNA. And you might have heard of that over the last 12 months or so, because messenger RNA is one of the it's the basis of some of the vaccines that have been developed for coronavirus. And the reason that they've been developed for vaccines is because the messenger RNA is read by the ribosome, which can then turn out proteins that are important for building the cell and for operation in the cell. So this messenger RNA tape is read by the ribosome, and the sequence of the building blocks in this messenger RNA, of the codons in the messenger RNA, tells the ribosome which amino acid to attach next to this growing polypeptide thread that then folds around to form the proteins in your body. It's an enormous molecular machine. It's got about 1 million atoms in every ribosome. And just the discovery of the ribosome led to the award of the Nobel Prize for Physiology and Medicine in 1974. And some 12 years ago, the Nobel Prize for Chemistry was given to Venki Ramakrishnan, Tom Stites, and Adi Yonath for their elucidation of the structure and mechanism of the ribosome. How can we make an artificial molecular machine that does anything like this amazing biological molecular machine? Well, this is a molecule that we made that does a tiny bit of what the ribosome does. It consists of a track, like the ribosome uses the messenger RNA of, with building blocks on it. And what we do is a catalytic chemical reaction that allows this ring to thread on the track. It assembles the track between it using a metal catalyst. We then add a reactive arm to the molecular machine and then set it going. And the ring moves down the track, detaches these building blocks from the track, passes them to an elongation site. The ring can then move further down the track. The arm can pick up another building block, pass that to the elongation site, and the ring eventually falls off the track, having built a new sequence polymer has grown off the using the building blocks that were on the track. And this is the chemical structure of the molecule that does that. And this ring moves down the track, picking up. These are amino acid groups that are on our artificial track. This is the catalytic group here, and this is the elongation site, and it forms this new peptide that has got a sequence of amino acids that corresponds to the sequence that they are on the track. So here we're using an artificial molecular machine to build, in effect, the building blocks of protein in the same way that biology does, uses RNA for. Now, why is that important to be able to build molecules with a specific sequence? Well, the reason is that in the molecular world, the sequence of how building blocks are put together is absolutely vital for function and properties. So in biology, all the proteins are just made from the same 20 building blocks. It's like Lego, and you've got 20 different building blocks, and you can build lots of different things with those 20 different building blocks. But the things that you build with them when they're biological building blocks, like amino acids, have completely different properties. So, for example, one thing that you can build is this polypeptide that is the cobra venom. That's an extremely toxic substance, but it's also being used as the basis for drugs to treat heart disease, hypertension, and high blood pressure. But take exactly the same building blocks, these 20 amino acids, assemble them in a different order, and you get myosin, which is the protein that generates the force in muscles. So just by taking the same building blocks, you can build something that's actually able to generate a force. Take the same building blocks, change their sequence again, and you get spider silk, a material that, although that it's just built of amino acids, it's 5 times stronger than steel. All that's possible just because you're changing the sequence of building blocks. And that's what molecular machines like the ribosome do. However, all of biology is in fact underpinned by just 4 different kinds of sequence polymers. Proteins, as we've seen, DNA that you'll be familiar with, RNA, and also carbohydrates, sugars. So all of biology just uses these 4 different kinds of sequence polymers to have all these different properties. We use in our technologies, we also use polymers like biology does, but we don't know how to make sequence polymers other than these biological ones. So all of the polymers that we use in our everyday world, polystyrene, polymethyl methacrylate, polyethylene, all of the plastics and materials that we use in our everyday world just work through they're based on one type of building block or 2 types of building blocks that don't appear in particular orders. Imagine that if you had polystyrene or polymethyl methacrylate that had the same diversity of properties as proteins do. That's something that we can't build yet. Chemists don't know how to do that. But biology uses molecular machines like the ribosome to construct those sorts of things. So maybe that will be something that can build artificial molecular machines to do. And this is the idea shown at the bottom of the slide for something like that, a molecular machine to assemble sequence-defined polystyrene that would have the same kind of amazing diversity of properties that proteins have. We've not done that yet, but those are the kinds of things that molecular machines will make possible someday. So this idea of using machines to build other machines is of course something that we already see in factories, where robots are used to build other objects, machines, like in this car factory where you can see the robots are being used to put together an assembly line of cars. And of course, one of the features of these kinds of factories is that you can program the robots to do different things, make different kinds of objects. And so this gives us the idea of, wouldn't it be amazing if we could make molecular factories that were had in them molecular robots that were capable of building different things. And in order to do that, of course, you would have to power this kind of technology. How can that happen? Well, again, we look to biology. How is biology, how is the nanotechnology of biology fueled? And it's actually fueled by using chemical fuels. All of these motor proteins, all of these biomolecular machines work by taking chemical fuels, something called ATP, adenosine triphosphate, and catalyzing a chemical reaction of it and using the energy from that chemical reaction to perform tasks. Recently, 5 years ago, we've learned how to do the same sort of thing. Again, this is the sort of thing that we saw with the paperclips. It's got this architecture that's the same of a paperclip, two rings interlocked together. And what we've been able to do with these very first motors, chemically driven motors, is make something where the paperclip, the ring, moves round and round. One ring moves round and round the other directionally. So you can imagine that they then be used as a pulley, say, to wind up, say, a polymer chain with a weight at the end, and or do some other kind of work. This is just a basic fundamental design of a motor. And the way it works, remember, these are molecules, so the components are moving randomly all the time. How this actually works is that you have blocking groups, these little red parts that block the backward movement that you don't want of the ring and get out of the way when it's moving forwards. And that's what actually allows the ring to move directionally round. So a little bit difficult to explain exactly how it works, but when you publish scientific papers, they are the science that you've done is assessed by other scientists called referees. They referee whether the work is enough to appear to be published and become part of the scientific literature. And when we published this work some 5 years ago, one of the referees came up with an analogy of how this system worked that we rather liked, saying that the design of this motor can be seen as the chemical equivalent of this grommet film, the wrong trousers, in which grommet, that's the dog here, is putting down track in front of this train as fast as the train travels. And the referee pointed out that in our design, it's working through the same sort of principle of having track put down in front of the train, but then also you need to have something removing track from behind the train so that it can't move backwards, and then it has no option but to move forwards. And we like this analogy of the referee so much that we had a picture made of our molecule as if it was a Wallace and Gromit cartoon. So the train here corresponds to the blue ring. The track going down in front of the train being put down by grommet, that corresponds to this building block being blocking group being removed. so that the train can move forward, the ring can move forward. And having a break in the line, that corresponds to this bulky group being in place, which stops the backward movement of this ring. And we like the picture so much that we actually had a short movie made of our molecule behaving like the Wallace and Gromit train. So breaking of the track, that corresponds to the blocking group being in place. Removal of the blocking group corresponds to the track moving down in front of the train. And as long as the chemical reaction occurs for this blocking group to keep coming in and being removed, then the little ring the train will continue to move around this molecular size track and be a molecular motor. And that's how we try and design these sorts of things. Then just a few months ago, we also made the first kind of chemically fueled molecular pump. And again, these sorts of things are important for the advancing of this kind of science, because we designed these things. And so for the first time, we have an example that explains, because we designed it, we know exactly how it works. And so for the first time, we have an example that explains how these kinds of motors and pumps can be designed. And this is an animation of how this actual pump works. It's got a track that we're going to pump these rings from solution onto, even though they're in a high energy state. And it's caused by a chemical reaction that occurs. This ring catalyzes, accelerates the reaction of the end of this track with this bulky group, which then stops the ring being able to move off. It moves over this sort of speed bump shown in green until it's on to the central region of the track. And this speed bump sort of blocks the ring from being able to fall off again, even when the end of this track is free. So then a second chemical reaction can occur to put a second ring on. Again, that can move over the speed bump onto the central region of the track. And once that's happened, the whole process can occur again, and a third ring can be threaded onto the track. And as long as we keep adding the fuel molecules, we can thread more and more of these rings on the track and pump those rings onto the track. Okay. So that's how we're going to we can fuel these molecular machines. What else do we need for molecular factories? We need them to be able to, the robots need to manipulate other molecular structures. And again, we've designed the first examples of molecular robots that can perform sort of rudimentary tasks. They're really, really simple, the ones that have been made so far. And this very first example was it's just a platform with a molecular robotic arm that's just able to pick up a molecular fragment and put it down on different places on the track. And this is showing a schematic sort of vision of how this actually works. We've got this platform here, and this molecular arm is able to pick up a molecule and put it down on a different part of the track. But we can program this arm to either pick up the molecule from the left-hand side and drop it on the right, or if we program the molecules differently, we can tell it to pick the molecule up from the right and move it around again and drop it on the left-hand side. It's only a rudimentary system, but it's the first example of being able to program molecules to move other ones around. And the great thing about molecular nanotechnology, of course, is that you're not doing this just on one machine at a time. You're simultaneously doing this on millions of machines, molecular machines, all operating, all doing the same thing at exactly the same time. And that's the great power of this kind of technology. So using molecules to build other molecules, to assemble other molecules, is this sort of science fiction idea that comes from science fiction that led this chap, Eric Drexler, in the late 1980s through to the 2000s to talk about molecular assemblers that gave rise to these ideas of grey goo and so on. The eyes of Drexlers are really based on shrinking down engineering concepts from the big world to the very small, which, as we talked about at the start of this talk, those sort of things really can't happen. It's a completely inappropriate kind of technology. You can't make things that look like this on the left-hand side. They simply can't function. However, there are things in biology that are like molecular assemblers, such as these super enzyme complexes, which are able to take building blocks and move them from active site to active site in enzymes and build other molecules. And so these things are a bit like molecular robots. And so we wondered whether it would be possible for us to use those as inspiration for building our own kinds of molecular assemblers. And again, that's what we've done. So we've taken the sort of platform robot that we saw in the last animation, where we had a platform and the arm was picking up the substrate and putting it down on various sites. Now what we're going to do is we're going to do chemical reactions on the substrate. So we have chemically reactive groups on the platform, and we can hold the substrate above either of these two sides and control that position by using this rotary switch, which controls the position of this robotic arm. And so it can cause the chemical reactions to occur either on the left-hand side or the right-hand side, which cause different things to happen. So if we hold it over on the left-hand side, we can first add a group by chemical reaction that we'll call new, stands for nucleophile. And then we could move the arm to the other side and do a second chemical reaction, which adds the electrophile that we'll call E. And that would have both the nucleophile and the electrophile adding to this substrate in a particular way to give this kind of molecule. However, we could carry out the same chemical reaction. We could program the molecule differently, the molecular machine differently, to add the nucleophile first on the right-hand side, and then add the second group, the electrophile, on the left-hand side, which would give us a different molecule here, a different molecule. Or we could do both of the reactions when the substrate is held on the left-hand side, or both of the reactions when it's on the right-hand side, and those would give us two more molecules. So those are all different molecules, and so there's 4 different molecules. We could choose which one of those was made by this molecular robot. And this is a video of how that happens. So this again is the molecular platform with these 2 different catalytic sites. The robotic arm takes the molecule, holds it over one catalytic site, it then switches it to the other reactive site, and that produces one type of molecule. However, we can also program the robot to do the reactions in a different order. We can do the first reaction over on the left-hand side, add the nucleophile, then switch it with the arm, add the other second reaction, the electrophile, and that will give us a different kind of product. Or, of course, we can do both of the reactions. We can program it to do both of the reactions on the left-hand side. That would give us the third sort of product. Or we can do both of the reactions while the substrate is held on the right-hand side, and that would give us the fourth kind of product. And again, it's not one molecule, not one robot, it's millions of millions of millions of these, all operating at the same time, all performing the same task. And this really works. This is the chemical structure. And by operating it, you can choose which of these molecules, 4 molecules, is made by this single molecular machine. And it works just like a computer program. You program what is the substrate that you want to get out, and that molecular robot will build it for you. So this is an example of where you can get each one of these 4 possible structures can be prepared selectively from a single substrate, the same building blocks, the common set of chemical reagents, all in the same pot by the programmed operation of a single artificial molecular machine. And when this was published in the journal Nature 4 years ago, Another article was written on it by these two scientists, Ross Kelly and Mark Stafford from Boston College, who said the idea of nanoscale machines that can assemble other molecules has long been thought of as the stuff of science fiction. Such a machine has now been built and might herald a new model for chemical synthesis. Science fiction becomes fact, and that is the state of the art of molecular robotics today. So I've used up way too much of my time. My apologies for that. I hope I've given you a bit of a vision of what's possible with molecular machinery. I haven't done any of this work myself. I have a fantastic team of PhD students and undergraduate students and postdoctoral researchers who have done all this work. I'd like to thank them for all their imagination and creativity. They're from all over the world, from China, from Belgium, from Romania, from Ireland, from Germany, from France. And this chap here, Justin, is known to Hamish. He's from the University of Adelaide, and he did a fantastic job for us for 3 years. He's now back in Adelaide working for a chemical company. And I'd like to give a special thanks to Justin for all his hard work and creativity during his time in our group. So what will technology be like in 40 years' time? Well, the Nobel Prize Committee for Chemistry, in their report in 2016, said that in a sense, we're at the dawn of a new industrial revolution of the 21st century. And the future will show how molecular machinery can become an integral part of our lives. About our work, they said the advances made have also led to the first steps towards creating truly programmable machines, and it can be envisaged that molecular robotics will be one of the next major scientific areas. Whether that turns out to be true, we'll just have to wait and see. Where's this going to be? Well, just like 125 years ago when they made the Model T Ford, I'm not sure they would have predicted that Glenn's car would have looked like this lovely Ferrari today. And similarly, it's 25 years since this just serendipitous discovery of this way of threading molecules together gave rise to molecular motors, things that can transport droplets across surfaces that you can see with your eyes, that can walk around tracks, and even molecules that can build now other molecules. Where's it all going? It's hard to say, but as we've said at the start, technology has always been driven by miniaturization, and molecular machines are the ultimate in that. And as this goes forward, they're going to revolutionize things such as transport, robotics, power, construction, and healthcare. But in trying to worry too much about how that's going to come out and what we should, with these, it will really come to be, we like to, in our group, to take a leaf out of Alan Kay's book. Alan Kay was one of the pioneers of the computer age. And in the 1970s, when there were always rumors flowing around about Apple are going to do this, IBM are doing that, Microsoft are doing this, Alan Kay said, the best way to predict the future is to invent it. And that's exactly what we try and do in our group. This is the city of Edinburgh, actually the so-called new town of Edinburgh that was built, all of it between 1785 and about 1820. So it's all in the same style. And for 10 years, my wife and I and our daughter lived here in Great Stewart Street. And if you walk down Great Stewart into Ainsley Place and into Murray Place, here into India Street, you get to 14 India Street. And 14 India Street was the birthplace of James Clerk Maxwell. James Clerk Maxwell was one of the three greatest physical scientists of all time, alongside Einstein and Newton. And that's because it was Maxwell who discovered that light was electromagnetic radiation with waves. And that's something of which Richard Feynman, the physicist that we heard about at the start, said years from now, there can be little doubt that the most significant event of the 19th century will be judged as Maxwell's discovery of the laws of electrodynamics. And that's an amazing thing to say, that the most important thing that happened in an entire century wasn't what a politician did, not a prime minister, not a president, not a king and queen, not a general. It was a scientist thought and what they gave to humanity. And you could say the same not only for the 19th century, but for the 17th century, the 18th century, the 20th century. And with you in the audience, it's your responsibility to make sure that the same thing happens for the 21st century. I'm sure that you'll be able to do it, to accept that challenge. So thank you very much indeed for having me. It's been an absolute honor to give the Stranks Memorial Lecture this year. And I'll leave you with this one final thought from John F. Kennedy, who stole it from George Bernard Shaw. Kennedy said, "Some men see things as they are and ask why. I dream of things that never were and ask why not." And that's the imagination that creative scientists can take to invent the technology of the next century. Thanks very much.
Thank you, Dave. We just feel absolutely incredibly lucky to have you present the lecture this year. It's a real privilege to have you as part of the collective here in South Australia for this event, and you've just I think you've revealed a world to all of us that like it was quoted, that the shift from science fiction to science fact. We can see every element of what we study in the chemistry through the molecular chemistry, the details in nanotechnology in those examples, and it's just to me, it's just incredible examples of how something that would appear out of reach to many is possible within our lifetime. So it just opens up a world of possibilities of how we could use this in really positive and amazing ways for the future. So we're absolutely indebted for you taking the time to be with us this evening. Really, we absolutely enjoyed it. So thank you.
Thank you. Thanks so much. My absolute pleasure.
We've got probably a few minutes to go. We don't want to take up too much of Dave's time today. If anyone had any really burning questions they wanted to drop into the chat, we might better maybe field a couple of questions before we conclude this evening. Well, the other possibility, if you raise your hand, I could unmute you as a participant. I think just lots of thank yous and praise in the chat.
Okay. Apologies if I not seeing the chat, but yeah, if you ask the questions or if Glenn asks them for me, I'm happy to answer anything.
Hamish, you had a question in particular.
Yeah, Dave, I was really impressed by that molecular machine, the fact that it's stereo specific. So I was just wondering, when you turn that on and off, I know that's a huge problem, is like having stereo selective reactions. When you go through that process, do you end up with 100% of one of those diastereomers or enantiomers in that mixture?
Yeah. So what Hamish is referring to stereo selectivity is the actual shape of the molecules, and it's very important. For example, in drugs, if you've got the wrong shape of a drug, especially the mirror image of them, they bind to the wrong receptors, and they can lead to all kinds of problems. For example, the thalidomide in the 1960s was due to having molecules of both handed deformities, and so it's a real pharmaceutical industry being able to make more. And our nano machines are the one so far in that example. It's not perfectly selective, it just biases. You get more of the molecule of the correct shape that you want. You can choose which shape that you want, and it will make, say, 75% of the molecules will have the correct shape. says my internet is unstable. Can you hear me okay? Okay, it seems all right now. You can get maybe 3/4 of the molecules you want will have the correct shape and the other quarter shape. So you then have to purify them to get.
Fascinating. Thank you.
All right. I don't think we'll push our luck with our bandwidth for much longer. I think we've got maybe one last question from, I know, a very keen chemistry teacher here in South Australia, Sandra. Sandra Eustace, I can see you've got your hand up there.
And I just put a question in the chat a little bit earlier on when you were first talking about moving molecules along the axis and you know, blocking the Teflon-like fluorines and so forth. Are we saying that a lot of that motion is because of the second? I know I've got some of my Year 11s listening, so I just wanted to, you know, maybe put it in context for them that we're saying that a lot of the forces that are in operation there are secondary forces such as hydrogen bonding that is causing that motion of the two molecule, the molecule with respect to the axial molecule along.
Yeah, this is a great point, Sandra. Thank you. Forces extremely important for how biology works, of course, and they're also important for molecules as well, because these although these forces are weak, they're a bit like glue, so they allow the components to stick in the correct places to do the job that they need to do. So, for example, in the one that I showed where right at the start, or the earliest example where we're moving the droplet along a surface, that works by the changing its position on the axle. And it does that by the manipulation of hydrogen bonding. It starts off with the fluorine atoms exposed because it's strongly hydrogen bonded to a region far away from where the fluorine atoms are. So the fluorine atoms are on the outside. And then what the ultraviolet light does is it actually changes the geometry of some of the chemical groups so that they become worse hydrogen bonders for the ring. And so the ring, it sort of unsticks from that other part of the axle and moves over to cover up the Teflon-like groups. So hydrogen bonding is absolutely crucial for the operations for all our molecular machines and how we design them. It's same true for the motors, everything.
It's wonderful for the students to hear that, you know, high-end chemistry, cutting-edge chemistry and molecular machines and so forth.
I'm not getting
still related to
sorry,
the.
I can't hear anything at the moment.
Oh, that's all right. Thank you for the answer.
I guess I'm frozen, am I?
Okay, so I'll, like I said, I think we're probably stretching the limits of our bandwidth and our luck, so we'll leave it there this evening. I just want to thank absolutely Dave and Hamish as well for his efforts in organising and participating this evening. We will make this recording available through the RACI website for those people who came tonight or those who registered but were unable to attend. We thank you all for participating in this 2021 Stranks Memorial Lecture. Thank you, everyone. We'll leave it there for this evening.
Thanks very much for having me. Bye. Take care, everyone.
Thank you, everyone.
Wear a mask.
Thanks, Glenn. Thanks, Hamish. Thank you, Professor.
See you, everyone.
Thank you. Bye.